Morning, everybody. Y'all got my email about the quiz? No quiz today. What did we say? Tuesday or Thursday?
Thursday.
Thursday, okay. So I written down Tuesday, and I wasn't sure what that meant exactly. So we'll do that on Thursday, and it'll be all of the current chapter that we're on, all of chapter 4. Just make sure you're reading that. Look for the big ideas in that chapter. The university is sort of not making plans, but just sort of thinking about what happens if, we just compete in class. So what that means for this class is probably that we will go to sort of online screencasting for the lectures for the rest of the semester, kind of like what I did. We'll miss that little bit of the chapter. I'm not sure what we'll do with the exam. Probably have some sort of online thing, or maybe you can move to a different type of assessment, like online exam. Very good, but maybe paper or something like that is fine. So we're actually not that far away from the end of the semester, though, and really a handful of weeks away. So we could, I'm sure that we can finish up the class online in some format that would be good for you. Okay? But I don't expect that to happen. But if it does, we'll be ready for it. We do have an exam coming up. It's actually not that far away. Today's the 10th, so we have 2 weeks from today we'll have an exam. And that will likely cover chapters all of 3, all of 4. Probably just 3 and 4. Yeah, just 3 and 4. And then after that we have, just one more exam after that. All right? Let's do a few clicker questions. So jog your memory about what we did last time. Which of these is not true for a longitudinal wave? We had transverse and longitudinal waves. So which of these statements is not true about a longitudinal wave? All right, let's stop at 50. Stopping at 50. Okay, good. A is right. Remember the longitudinal wave, transverse wave is what you usually think of, an up and down wave, like waves in a lake or on the water. A longitudinal wave is when the medium moves back and forth. That was like the hug wave that y'all did that you liked so much. You remember the hug? So that's a longitudinal wave. Which of these is the wavelength of this transverse wave? And when I'm looking at this, the axes on this graph are y and x. And which of these show the wavelength of this wave? All right, I'm going to stop at 38. 38. Okay, B is the right answer. So with a wave, you're starting at one point, and then you go through one full cycle of the wave. That doesn't mean that you go here. That would just be a small portion of it. It means that you go all the way back to where you started. So notice right here, I'm starting at this point, and I'm going up. After I travel one wavelength, I'll be at that point, and I'm going up in the wave. So it's one full cycle of the wave. So you'll go actually through one point on the wave, and then you'll go to the next point on the wave. What kind of graph is this? Is this a snapshot, or is this a history graph of a wave? Is it a snapshot of a wave, or is it a history graph of a wave? Snapshot or history? Oh, come on, y'all are like evenly split. Ask around, ask your neighbors what they put. This is a y versus x, shows the y position versus the x position. Ask your neighbor what they put, okay?
All right, let's stop at 38. Hey, Deshaun. Okay, good. That's a lot better. This is a snapshot. You can tell the difference because a history graph would have Y, but instead of X right here, it's going to have T. That would be a history graph. You know, history has to do with time. So a history graph shows the progression of that wave through time. But a snapshot graph just shows, you take a picture of it, like a snapshot, and it shows what the wave looks like in all positions, in all two-dimensional positions, in the Y and X positions at that particular point in time. All right, the velocity of a wave is 2 meters per second. Its period is 2 seconds. What is the wavelength? Oh, did we do this? I don't remember talking about this. I'm gonna show you what the answer is. So we had that equation that related the velocity and the frequency and the wavelength. They looked like that. Remember, we said that the velocity of the wave is dependent upon the medium, and then so this remains constant unless you change medium. And so, like if our wavelength goes up, that means our frequency goes down. So low frequency sounds have a long wavelength. But then there's another expression for the speed, and it is a function of the wavelength over the period. So here, if my velocity is 2 meters per second, that's going to equal to my wavelength divided by my period, which is 2 seconds. And so the wavelength is going to be, what is it going to be? 4. It's going to be 4. So B is the right answer. I don't know if I wrote down this equation. We said it in words, but I'm not sure if I wrote that down. Did I write that down? If I didn't, make sure you write it down. It's an important equation. This is just saying that a wave travels one wavelength in one period. I know for certain I said those words, that a wave travels one wavelength in one period. And that's expressed in this equation. The speed of the wave is the wavelength over the time. Okay, the loudness of a sound. I don't know if I said this either, actually. Okay, yeah, B is right. The loudness of a sound is affected by what? Not sure if I said this either, I'm sorry. But intuit the answer. I think you probably, intuitively, I think you can know the answer. And we'll come back to this later. Okay, good. More of you have it than don't. Ask around. Ask your neighbor what they put. They can be very useful to you sometimes. Nobody's asking your neighbor. Okay. Let's stop at 45. 45. Okay, I can see why you think the frequency might affect the loudness, because higher frequency sounds tend to, I don't know, hurt our ears more. But in fact, the loudness is only the amplitude. So remember, with a wave, if I'm looking at, well, either a snapshot or a history, the amplitude is this value right here. So if I'm looking at a water wave, for example, how high the wave goes tells me what the amplitude is. And in a sound wave, too, the amplitude is given by the height of the crest. Often on a graph, this might come up in some of the tests as you're looking back at old tests. Sometimes you don't have this axis, and so what you have to do is you have to measure this distance, and this would be twice the amplitude. So you would measure that distance on your graph and then just take half of it. Sometimes that's the easier thing to do. Okay, let's talk about a mass spring system. This becomes important. It's a nice example of simple harmonic motion, which is simple harmonic motion occurs when you have, do you remember, what do you have to have simple harmonic motion? Think about it, and I'm going to draw a mass spring system, and maybe that will give you a clue. as I draw the spring, which is going to provide something that's very important for simple harmonic motion. It's two words, starts with an R and an F, the second word. Not everybody all at once. What's important for simple harmonic motion? A restoring force. Yes, thank you, Anna. So a restoring force is really important for simple harmonic motion. All waves have some sort of restoring force. That is a force that will restore the system to its equilibrium position. And for a mass spring system, you know, it is the force that is applied by the spring. So that spring will cause the mass to come back to its equilibrium position. The frequency is given by this for a mass spring system. It's 1 over 2 pi square root of k divided by m. And here k is the spring constant. It describes how stiff a spring is. You ever take those little clicker pens apart? Ever take those apart? You know, it has that little spring inside of it, right? You ever shoot it across the room? Like you take the pen apart and then you like pull it down on the thing, and then it shoots way across the room. Just me and Maddie, that's it. Yeah. You ever seen the springs on your car? Those big springs that swirl around your shock. Do you know which of those has a bigger spring constant? The little spring in your clicker pin or the spring in your car? Which of those has a bigger spring constant? If you're ready to guess. The stiffer spring has the bigger spring constant. So which is it? The car, right. Not a trick question. The car is a much stiffer spring. And so it takes a really big force to take it out of its equilibrium position, which is good because your car is kind of heavy compared to the force of your thumb on your clicker pen. So different springs have different spring constants. The stiffer the spring, the bigger the spring constant. And here m is just the mass of the object. This restoring force, by the way, is related to the spring constant. The restoring force is equal to k times x, where x is the amount that the thing is displaced. So if I displace this block down to this position, then that's going to be x. So the more that I stretch out the object, then the greater the restoring force will be. This is a rubber band, right? If I pull on it, the restoring force is whatever it is. So if I pull on it more, what happens to the restoring force? Does it get bigger or smaller? Well, I don't know. Let me top somebody with a rubber band. If I pull it back, I'm not going to do that. But if I pull it back just a little bit, right, it's not going to have much oomph to it. But if I pull it back really far, does it have a bigger or smaller restoring force now? It has a much bigger. Oh, it went a long way. Okay, so if I increase x, then that increases the restoring force. That's sort of what you think of, right? I think you don't intuitively know that. But if I stretch out a spring more and more, then the restoring force F will increase more. Okay, so I want you to notice that the length of the spring is not in this expression. So if I have a longer spring, doesn't really matter. That it's really just dependent upon the material that the spring is made out of. And stiffer springs also give a higher frequency. We'll see that later. You can sort of see it. If I stretch out this thing, the material actually gets a bigger, like if I stretch out the rubber band, the material will get a bigger K value. And if I stretch it out and then I pull it like this, then it's going to have a bigger restoring force, as opposed to if I have it like this, where it's not quite as stretched out, it's easier for me to pull out. So if I stretch the rubber band, then the actual K value will increase given a different force. So if I increase K, the frequency will increase. You hear the frequency? If I decrease, the frequency decreases. We'll see that in a bit. But Sarah?
Is it the length of the link or the length of the spring?
The length of the spring.
Oh, okay.
Why would they length of the link?
That's what you wrote.
Yeah, the length of the spring is not in this expression. Okay? I'm sorry, what? Are you serious? That was enough? Okay. I really just show you this equation now. It's important, but we'll see another equation as it relates to the human body later that's almost identical to this one. Okay? Oh, and it's going to be right here, actually. For a vibrating string, like on a guitar, the frequency is going to be really similar. That frequency is 1 over 2L, the square root of T, divided by mu. And let me show you what these different things are. Mu is the mass density. Mu is a Greek letter, a lowercase Greek letter for mu, as in like phi mu. Any phi mu's here? No phi mu's? No? Anyway, it's a Greek letter, and it stands for the mass density. It's a measure of mass per unit length or kilogram per meter. It's sort of like volume density, except it's a one-dimensional volume density. So how much mass do you have per unit length, as opposed to per unit volume? L is the length, and then T is the tension. And sort of like I said with the rubber band too, that if I apply more tension, then that increases the frequency of the restoring force. So I want you to know how the frequency varies with these different variables. If the tension goes up, if the tension increases, what happens to the frequency? Does it go up or down? It goes up. So if the tension increases, the frequency goes up. In fact, if my tension increases, say, by a factor of 4, by how much does my frequency increase? If I increase my tension by a factor of 4, by how much does my frequency increase? Well, whatever I do to the right-hand side, I have to do to the left-hand side. And here I'm multiplying this times 4. Do I get a factor of 4 over here? What? No, it's not 8. I appreciate that. It's not 4. I know what it is. It's 2. Because I'm doing what to the right-hand side? To T. It's the what of T squared? The square root, right. And so whatever I do to T, I also have to do to the factor. So I take the square root of 4. And whatever the square root of 4 is, will be how much my frequency increases. So if I multiply T by a factor of 4, then that'll increase the frequency by a factor of 2. That is that the frequency is proportional to the square root of T. All right, if mu increases, that means that the frequency decreases. Y'all play stringed instruments? Piano, guitar, ukulele, yeah? So have you ever seen the lower pitched strings on any of those instruments? What do they look like? They're thicker, right? They have a bigger what? They have a bigger diameter. They have a bigger what in this equation? Tension. No, they actually don't have a bigger tension. They can have the same tension, or they might even have a lesser tension. But the physical property of the string is different in what way? It has a different. It does have different length, actually. Yeah, that's not what I mean. Huh? No, not wavelength. It does, though. Like it produces a different wavelength of sound. It has a different mass density. Right? A big, thicker string will just have more mass per unit length. So like a bass guitar, for example, those strings are a lot bigger, just bigger around, than they are on a guitar, on a 6-string guitar. And likewise on a piano, the lower strings are much bigger in mass density, also in length. Who said length? Brittany? Yeah, they're also longer, you're right. But they have a much larger mass density. So if mu goes up, the frequency goes down. And then also if the length goes up, the frequency also goes down. So understand how those variables are related to one another. By the way, the length, if you look at a guitar, can I draw a guitar? No, I'll just draw the strings. If you look at a guitar, the strings are actually all different lengths. That's why the neck of a guitar, the keys are all sort of, like the tuning keys are all at different positions because the strings are different lengths. So which of these strings would be the lowest pitched, the top or the bottom? The top will be the lowest pitch because this is low frequency and this one is high frequency. Okay? If there's an inverse relationship between length and frequency. Okay, let's try some of these questions. The spring constant describes what of a spring? Okay, let's stop at 37. 37. Okay, good. B is right. The spring constant describes the stiffness of the springs. Like the springs on your car have a much higher spring constant than the springs on that little spring in your clicky pin. It's just a much stiffer spring. On a piano, the highest pitched note, the ding, 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 on your piano comes from which strings? The longest strings or the shortest strings? Even those of you who play pianos, you don't have actual pianos, do you? Anybody play, who plays piano here? Do you have an actual piano or a keyboard?
Yeah. I have like a piano that has all the keys.
Okay, yeah, that's what I
It's
have.
like closed, like I can't open it to see.
Oh, you can't see this.
Oh, it's an upright?
Yeah, we used to have one of those, but then we moved and we got rid of it and we got a
You
keyboard.
want the very top, you can look in, and
Uh-huh.
the strings line at a different angle.
Yeah. Yeah, we had one that was called a spinet. So the strings go up and then down and then up again. So it's not real, it's a smaller one. Anyway, let's stop at 55. I miss our piano, though. Like a keyboard just doesn't really recreate the sound of a piano nearly the same. I miss it. They told me that it would. Whoa, look at you. B is right. Yeah, so the highest pitched notes come from the longest strings. Hey, what is Mozart doing? Right? What? Right, shortest. What is Mozart doing right now? Decomposing. Actually, he's probably long decomposed. Okay, so let's look at pressure waves. These are sometimes called compressional waves. Sound is a longitudinal wave. The medium in a longitudinal wave moves what? Up and down, back and forth. Back and forth. So remember, you'll probably have a question about longitudinal versus transverse waves, and that's the main difference. They both have wavelengths, they both have frequencies, they both have amplitudes, but the transverse wave moves up and down, the longitudinal wave moves back and forth. And sound is a longitudinal wave. The medium moves back and forth. And this causes big and small pressures in the medium. So it's like with the spring. Remember I showed you the spring where we had the spring where we'd send a longitudinal wave. Did I do that with the spring down the middle of the classroom? Yeah, so what you get is you get regions of high pressure and regions of low pressure. The regions of high pressure are where the spring gets really close together, and the regions of low pressure are where the spring is far apart. So this is high pressure right here, and then this is low pressure right here. Those regions of high pressure are called condensations. And the regions of low pressure are called rarefactions. Okay? Condensations are right here, rarefactions are right here. And that's true for sound waves too. That it was true in the spring, but when you make a sound like that, that sound propagates through the medium, through air, and it's a region of high pressure, a region of low pressure, a region of high pressure, a region of low pressure. And depending on the quality of the sound or the type of the sound, those rarefactions and condensations are going to be close together, or they're going to be far apart. What do you think, what kind of sound is it going to be if the rarefactions and condensations are really close together? What kind of sound do you think that would be? Let's do that as a clicker question. I want you to think about it. If the rarefactions and condensations are really close together, is it going to be a high-pitched sound, or is it going to be a low-pitched sound? If the condensations and rarefactions are close together, is that a high or a low-pitched sound? Oh, good. Okay. Let's stop at 30. Good. A is right. That is a high-pitched sound. So if I were to draw, say, a transverse wave, we often represent, well, if I draw the history graph for a sound wave, the high-pitched history graph would look like this. The low-pitched history graph would look like this. Okay? So in a high-pitched sound with a high frequency, the peaks of the waves are all scrunched together. In a low-pitched sound, they're all stretched out. Okay? Remember frequency. We defined frequency early on as frequency is equal to 1 over the period. And so if the period is small, that means I have a high frequency. And remember, the period is the time for one full wavelength. And so on this is 1 period, which is a relatively small time. But on this one, this is 1 period. So say here, 1 period, 1 period. And so the period for a low-pitched sound is really big. It just takes a long time for that wave to make it through 1 wavelength. But the period for a high-pitched sound is really short. That gives a high frequency for this wave and a low frequency for this wave, because the period is small for this wave and big for this wave. Big frequency, small period. Small frequency, big period. They're inversely related. This feature of pressure waves is an application of the ideal gas law. We saw the ideal gas law last chapter, I think. We wrote it. You can see the ideal gas law in a couple of ways. We wrote it last chapter as NRT. I think your book in this chapter actually writes it as PV is equal to NKT. The P, V, and the T are the same. It's just the N and the R, or the capital N and the K, those change, but it's the same equation. And these two variables just talk about the amount of gas. But what it's saying basically is that if P increases, then the number of molecules N will increase. And so that's true for compressional waves, or for longitudinal waves, or pressure waves, that when you get more things condensed down into an area, like you do with a sound wave in those high pressure areas, then you have more molecules of gas. So if I were to draw a picture here, I'll just sort of draw the spring again. That here I have a lot of N. So I have a big N. That means I have a lot of molecules. And because I have that, I also have a high pressure. So if my N value increases, then my pressure also increases. Your book talks about that in a bit, just how we apply the ideal gas law in these compressional waves, that the amount of gas increases, the number of molecules increases, so that means that the pressure also increases. Here we have that again. So the number of molecules in a particular region increases. That's N. So the pressure increases. Sound can also travel through solids and liquids. While it is still a longitudinal wave, longitudinal, we don't call it a pressure wave. Because it doesn't really change the pressure of the medium. Remember back in chapter 3, I think, was that 3 or 2? 2, when we talked about fluids, we said that some materials are compressible and some are not compressible. Which fluid is compressible? Which fluid is compressible? Fluids comprise of liquids and gases. Gases are compressible, right? And liquids are not compressible. Are solids compressible? As if you press on a solid, does it change its volume? No, by definition they're not. Like you might break the solid or whatever, but they're not really compressible. So when we talk about longitudinal waves traveling through a solid, we don't really talk about them as pressure waves just because they don't change the pressure of the material. But nonetheless, they can move through a solid. All right, we'll continue that with the speed of sound. That'll come back, that idea. So sound travels at different velocities depending on the medium. And the speed will depend on the elasticity of the medium. A more elastic medium has a higher speed. Let's say that I have some material. It's made up of a bunch of different molecules. Remember how we said for simple harmonic motion you have to have a restoring force? If I displace one of these molecules, say I pull it out of place a little bit, there has to be a restoring force that acts to move it back into its position. And the bigger the restoring force, the more elastic the material is. Often we hear the word elastic and we think, how stretchy is it? But when we talk about a material being elastic, it means that it has a very large restoring force. If it's the more elastic it is, if you move one of its molecules to a different position, then there'll be a big restoring force to push it back into that position if it's a really elastic material. So with that in mind, I want you to guess or make a decision about what has a higher speed of sound. Because the speed of sound will depend on the elasticity. The higher the elasticity, then the higher the speed of sound. Is the speed of sound higher in a gas, or is it higher in a solid? Or really I'm asking, which of these materials has the higher elasticity? Whereas if I move one of its molecules out of place, it'll have the higher restoring force to put it back into place. Two questions, they have the same answer. Which has the higher speed of sound? Or which is the more elastic material, a gas or a solid? Which has a higher elasticity? Okay, I'm going to stop at 40. Okay, A is not right. B is the right answer. And the reason is that you're thinking about elastic in sort of the way that you think of elastic. The elastic is like something stretchy. And so you think, oh, well, a gas is sort of stretchier than a solid. And so a gas isn't really stretchy. But if you think of a gas and a solid, you can move the gas around more easily. So it's like it's sort of stretchier. But elastic does not mean that when I talk about it in terms of physics and sound. That elastic means that if I take a molecule or an atom of that solid or gas and I move it off to the side, what forces are there going to be that will put it back into place? And if I take a molecule of gas and I move it over here, the gas doesn't really care. If I let it go here, it doesn't rush back to this position. Because there's not really, watch, you ready? It's like the Karate Kid. Y'all watch the Karate Kid from the 80s? Where he catches the fly with the chopsticks. If I take a molecule of gas and I move it over here, very little restoring force. It's not going to move off to the side, or it's not going to move back to its original position. But if I try to take a molecule of this desk and move it off to the side, first of all, it's really hard to move it because the restoring force is so darn high. Right? It's bound up within its material. If I move it, then it's going to move back. So when I make a sound in a solid material, it's going to travel really, really fast. Because as it moves through that solid, it displaces the molecules just a little bit, and then they move back really quickly. And so the speed of sound in a solid is much, much, much higher than the speed of sound in a liquid or a gas. So the elasticity of a medium describes how quickly it returns to its equilibrium position when displaced. A spring with a high spring constant that's K, is very elastic. And again, not really the way that we use elastic, because we think of the little clicky pin with the spring in that. We think of that as being elastic, but it's really the opposite, that the spring in your car is actually more elastic. Which is most elastic? A solid, a liquid, or a gas? Oh, come on. Ask your neighbors. Ask your neighbor what they put. Okay, good. Good, good. All right. I'm going to stop at 15. Okay, good. A is right. So the more elastic of these is the solid. And then also the speed of sound is highest in a solid. I'll show you some numbers here in a couple minutes. Is highest in a solid. So steel is one of the most elastic materials. So we can compare their various speeds of sound. In water, the speed of sound is about 1,500 meters per second. That's about 3,400 miles per hour. In steel, on the other hand, it's 11,400 miles per hour. So more than 3 times the amount. And in air, it's just a paltry 760 miles per hour. Okay, so if I'm looking at the elasticity, or the speed of sound, it's going to be air, water, and then steel with the highest. Solids and liquids have much higher speeds of sound than air or other gases. All right. Can I go down from here? Good. So in a gas, you can change the medium to alter the speed of sound. If you change the medium, if you change the gas, you're effectively changing the medium, and you're changing the properties of that medium, how big the molecules are or the atoms, and then that affects how quickly gas will move, or sound will move through that medium. Small molecules move more quickly. So sound travels faster in those materials. So let's try some of these. We're going to try this first top one. In which of these does sound travel faster? Does it travel faster in helium, right here on the periodic table, or does it travel faster in air, which is a mix mostly of nitrogen and oxygen? In which of those does sound travel faster, in helium or in air, which is nitrogen and oxygen? All right, let's stop at 48. Okay, good. A is right. Why does it move faster in helium? What is it about the helium? It has a much smaller mass, right? It's like 4, and the others are like 15, an average of 15 smaller mass units. So the helium is a much lighter atom, and that means that it can move a lot faster. So when a sound wave travels through, it's like it has less inertia. Like the sound wave hits the helium atom, it moves out of the way, and then it moves back really quickly because it's so much smaller. In which does air travel, or which does sound travel fastest? Air, water, or wood? Okay, and I'll stop at 15. 15. Good, C is right. Wood, I know it seems like sound doesn't travel very fast in wood, but it actually does. It's a solid, so much like steel. It's not going to be quite as fast as steel, but it will still travel through that material a lot faster. You can experience the sound traveling through a solid or through a liquid. In a liquid, you can just go down into a pool,
and you'll hear sounds as they travel through. Or if you have somebody that's trying to talk to you underneath the water, you ever tried that? It's kind of difficult actually to talk underneath water, but you can make sounds regardless. Or you can tap the end of, say, a long metal pole and put your ear next to it. You can hear the sound as it comes through.
True or false? Sound travels faster in a gas with a higher temperature. You don't know I haven't told you this, but I think you can figure it out. So, does sound travel faster in a gas with a higher temperature? Is that statement true or is it false? By the way, this was from an old test question, but I don't give true false questions anymore. I think they're confusing. Are they confusing, true false questions? Yeah. But I do want you to know if sound travels faster in a gas with a higher temperature, I'll just ask it in a different way. Okay, maybe it's not so intuitive. I'll talk about it. We'll stop at 35. A is the right answer here. But if you think about a gas at a higher temperature, what's true about those molecules in a gas at a higher temperature? They're moving a lot faster. That if the temperature of our gas increases, that means that the molecules are just moving around already at a lot faster speed. And so as a sound wave comes in, it will sort of capture some of that speed and it just travels faster because the molecules are already moving faster. So sound does travel faster in a warmer material or a hotter gas. So it moves faster in a gas with a higher temperature. That's true because the molecules of the gas are moving faster. In a higher temperature gas. All right, let's see. I have a video I want to show you. This is just sort of basics of sound stuff. All right. So breaking the sound barrier. Breaking the sound barrier. This was first done by Chuck Yeager in 1947. And later this was done by a land vehicle. That was in an aircraft. But later this was done by a land vehicle. It was actually like a jet-powered car. I'd have a video for it. Unfortunately, they took it off of YouTube. So, but it's a land vehicle. That was in 1997 by a jet-powered car. Actually, let me see if it comes up. Maybe it's back now. No, they took it away. Sorry. So the sonic boom is very similar to the wake of a boat. The boat travels at a speed that is larger than the speed of the water waves. And so then the waves, they can't get out of the way, basically. And they add up to produce the wake that's seen on the shore. And that wake is bigger than any individual wave because they've been sort of collecting up upon one another. And so a sonic boom is largely the same. So if we think about a boat, it has a velocity that's bigger than the speed of the wave. The boat does. And so it's producing waves, but the waves are traveling faster, or excuse me, they're being produced at a rate faster than they can travel to get out of the way. So these waves will tend to collect upon one another, And when they collect upon one another, if I have two waves like this, if I add them up, what's going to happen is that they'll make a bigger wave. And so this bigger wave is the wake of a boat, or it's going to be like a sonic boom. You ever seen, what's the name of that? Frozen Planet? I have a clip I want to show you that. This is called, that demonstrates this principle. This is called interference, where I can add up two waves and they make a bigger wave. This will come up later when we talk about noise canceling headphones. It's a related idea. And the same as for a sonic boom. So sonic booms are really just a collection of these bigger waves, where I have two or more waves that add up because they can't get away from one another, and then they produce this much bigger wave. A bigger amplitude wave has a bigger volume. There are also a number of visible effects due to the pressure variations of a sonic boom. Your book talks about those a bit. Okay. Let's look at the production of sound. So sound waves are created by some object that pushes on the air. For example, a speaker, a tuning fork, a spring, or like the rubber band, right? It makes a sound. The tuning fork. Let's see, I think I brought one. So this is a tuning fork. It has a frequency of 426 hertz. If I strike it, then it makes a sound. You can pass it around if you want. You can see how it makes the sound, and then you can also feel sort of the vibration. Yes, you can pass this around and just take a look at it. A simple wave has a single frequency, and the tuning fork has a single frequency. That's the whole point of a tuning fork, that you have this object that creates this very defined frequency. A simple wave has a single frequency, like a tuning fork. And a complex wave, on the other hand, has multiple frequencies added up. So your book has a figure. Does anybody have their book with them? Yeah. Yeah, so it has a picture of a simple periodic wave and then a complex periodic wave on page 113, but it's similar to what I have on my book. The way you get a complex wave is by adding up multiple waves. So if I add up, say, a wave like this, and then a wave like this, and then a wave like this, notice that these waves are all sort of offset from one another. Then you can get a more complicated that might have more frequency variations within it. So it's more of a complex wave. A complex wave just has lots of frequencies that are mixed up within it. Let me show you an example. I'm going to stop there. Oh, no, I can keep the recording. Show you an example of this. This is kind of cool. I'm just going to search frequency generator on YouTube. Oh, where is it? This online tone generator. What this allows you to do is to create tones of different frequencies. So this is about the same as that tuning fork. That's about the same as the tuning fork. Or actually, I think it was about 430. What was? Mhm.
That is simply like disrupting the vibrations.
No, so that's a good point. So when you hit the tuning fork, y'all try this, Maddie. When you hit the tuning fork, sort of move it around back and forth. We'll see this a little bit later. That has to do with Doppler shifts. Can y'all hear it? Hear how it changes frequency? Because if the source of your wave is moving, then it's going to cause the wave to have a different frequency at your perception. It's like a police car coming towards you. You hear it coming towards you, and it sounds different than when it goes away from you. It's the same effect. It's called Doppler shift. All right, so I can use this online tone generator to mix up multiple frequencies. So there's my 440. Oh, sorry. Is that annoying? Sound. I'm going to mix it with another tone. So now that's the 438 and the 440 together. I can add another tone. And so it can make, if you add a whole bunch of different frequencies, and a musical instrument has a lot of different frequencies, even at a single note, it can have multiple frequencies. It'll make a more complex and rich tone. Okay? We'll come back to that frequency generator later, because it turns out that the human ear has a particular range of frequencies that you can hear. We'll explore that with that. Okay? A couple more things. So detection of sound. I forget what I had in my notes here. I'm sorry. It involves something of something. And I have lines here and note to myself to go back and look to see what I had intended there, but I forget. But it involves something of something, sound. But a device measures the frequency and amplitude of the pressure wave in a medium. So anytime you have a device that detects sound, like a microphone, all it's doing is it's detecting the amplitude of that pressure wave and then also the frequency at which the pressure wave comes. So you need to have something that will move further if the amplitude is bigger, and that's what a microphone does, and then is also sensitive enough to get all the different pressure variations in a wave. A microphone, an ear, are two ways to detect sound, not the two ways, but two ways to detect sound, and both consist of a diaphragm that vibrates when a sound strikes it. So this is a figure of a microphone. Just have a diaphragm. It's a material that's stretched over a surface. Or, you know, a speaker is really just a microphone, but that instead of detecting sound, a speaker produces sound. A speaker and a microphone operate by the same principle. So the diaphragm, when a pressure wave comes onto it, it makes this thing vibrate at a particular frequency and with a particular amplitude, and then it converts that into an electrical signal that you translate into some other sound. A microphone and speaker are very similar. So the speaker is like this cone that vibrates back and forth, and then that produces a wave. And the microphone is something similar, where you have this diaphragm where when the wave comes onto it, it causes this thing to vibrate back and forth. So a microphone is really just the opposite of a speaker, or the reverse of a speaker. It does exactly the same as a speaker, but just in reverse. Instead of producing sound like the microphone does, or producing vibrations, the microphone will actually detect vibrations. But both of them are going to consist of a diaphragm that will vibrate back and forth, either producing or detecting sounds. All right, I think we'll stop there. The next part is our A and P section. Next time, we'll start with the quiz, okay, but it'll cover the entirety of that chapter. So make sure you read the second part of the chapter. Just looking for big ideas, okay, so make sure you're looking for those in your book. Have a good day. Good to see you.